Welcome to EDU World Space.
Here we have a beam that is, let's see here, is simply supported at, is pinned at the left end. Has a couple of pin joints along the beam, so it's segmented into three sections. There's roller supports here and here, and then there's another roller at the right end. So in this case, we have a linearly varying distributed load over the first segment and a uniform distributed load over the other two segments. At these pin joints, there is no moment being transferred across them. So we can do free body diagrams, analyze free body diagrams of the entire system and then any two of the subsystems to get the equations for the six unknowns, 1, 2, 3, 4, 5, 6. In this case, the reaction force here, and these are really all that we need to get the shear and moment diagrams. So the reaction force at the left end comes out to be 6.75 kilonewtons. In the middle, on the left side, we have 36 kilonewtons. On the right side, we have 49.5 kilonewtons. And on the support at the right end, we have 18 kilonewtons. Now, the first segment is 4.5 meters long. Because we have a linearly varying distributed load, the shear will be a quadratic function. It will have a slope that starts with 0, and it will start at a value of 6.75 kilonewtons. And the parabola is given by this function. And until we get to 4.5, which is here, we are on this parabolic curve. At that point, we cross into the region where we have a uniform distributed load. Since that's 9 kilonewtons per meter in the negative direction, we have a slope of negative 9 kilonewtons per meter in this region here. So this is linear here. Again, because there's no jump in shear, they need to be continuous. We could figure out what this value is here by just looking at what the shear force is at 4.5 meters, which looks to be about 15 kilonewtons or so. Then when we get to this point, we jump up 36 kilonewtons, and we continue along after. So in this region we're here, we jump up here, and then in the region between the two interior supports, we have a slope of minus 9 kilonewtons per meter. Then we jump up 49.5 kilonewtons. And finally, in this region, we have, in this region and this region, we have a slope of minus 9 kilonewtons per meter. And we end up with a value of minus 18 kilonewtons, which corresponds to this support load here. Now, the moments are pretty messy, and again, we can get them. Either we can get them by taking integrals of these functions, and then finding the constants of integration so that the moments match. Again, the moments need to be continuous in this problem because there are no point moments. In the region, in this segment of the beam, we have a cubic function, which we can see is the integral of this function, and the constant of integration is 0 because we have a moment that is 0 at the left end here when x is 0. So in this region here, the function is given by this. Then and we can see that it goes through 0 at 4.5 meters because we have no moment transfer across this pin joint here. So that checks. In this region, we can see that we can again get our moments. We start at 0, and our function is given by this expression here, which is quadratic. and it would be the derivative or the integral of this function here, defining this curve. So we can see that we have 4.5 minus 4.5 in front of our x squared term instead of 9. So if we take the integral of minus 9x, we get minus 4.5x squared, which confirms that. And then again, there's a constant in this function here, and that would actually be 27. And then again, this constant of integration we can determine by making sure that this function at x equals 4.5 meters is 0. So until we get to the point load, we have this function, and then when we get to the in between these supports, we have this function, which is again quadratic. Again, notice the coefficient in front of the quadratic term is minus 4.5. Again, we can find this constant by making sure that the functions agree at this point here at, let's see, that would be 6.5 meters. And we get to this point, and then for the end region here, well, for this whole region here, basically, we have this function here that describes it. And again, notice we have a coefficient of 4.5 in front of our x squared term, because we had a coefficient of 9 in front of our x term here. Again, if we take a derivative of this, we should get this. So in fact, the function here would just be 112.5 minus 9x would be this function here. And then we have this coefficient, and then again we can make sure that these functions agree, the values agree, this and this, at this point to find this constant. And then when we plot this, again, we can have a couple checks on this. We can make sure that, again, that it goes through 0 at, where are we at here now, 10.5 meters. So at 10.5 meters, the moment should be 0, and in fact, it is. And then also at the end, at 14, let's see, is that 14? Yeah, 14.5 meters, it should also be 0. And in fact, if we plot this, that is correct. So everything checks here. Again, that doesn't necessarily mean the answer is exactly correct, but it passes all of the kind of sanity checks on what we would expect we would expect the answer to look.